I have started the recording. Okay, so it's recording now. Welcome everyone to this second meeting of our weekly seminar on quantum information. And this week, as speaker, we have Sahil Naik, who is a PhD student in the quantum information group of Dr. Manik at SN Bose National Center for Basic Sciences. And Sahil is at a very advanced stage of his PhD, and he's a very good speaker. So we have invited him to give this 2-week series on process matrices, formalism. And I would like to remind all of you that we are hosting these sessions to encourage discussions and possibly later collaborations. And so everyone is encouraged to ask questions with Sahil's permission, maybe during the talk or maybe after the talk. He can say like whatever he prefers. Okay, so I will start. Over to you, Sahil.
Yeah, so thank you, Shona. So you can see the screen, right? The full PPT. It's visible, right? The full screen.
Yes, yes. We can hear you and we see the screen.
Yeah, okay. So thank you for giving me this opportunity to present today. So Mirza asked me to present from a very beginner's point of view for this process matrix formalism. So I will not be going into the recent developments of this field, but I want to give an introduction to the beginning papers that came in this field. So let me start. So I will. So Nita also asked me to see if I can discuss some new problems that we are currently thinking of in our group. So that if I get the time for that, I will be discussing some paper based on which we are discussing these problems. Then I will discuss it today. Otherwise, I can continue it in the next week. So yeah. So the title is this: process matrix frame formalism from perspective of higher order quantum theory. So what is higher order quantum theory? That is the first thing what we want to understand. So before going into the exact detail of this thing, so let me draw a picture which maybe most of you have seen before. So when you think of some localized events in space-time, you have some picture like this in your mind, where you have maybe, let's say, two different events, where one being in the past of the other, or vice versa, or they can be space-like separated. So if I call these events A and B, so these are the three possibilities that we can have. So this squiggly symbol means they are space-like separated. So this is what we call a relativistic notion of causality, where we describe our space-time as a bunch of points, and we have causal relations between pairs of points. So and the relation can be of these three types. So this is what Einstein was talking about when he was talking about causality. This is the notion he has in his mind. This is the notion we use in special relativity or general relativity. But we are coming from an information theory background. So there is also this notion of theoretic notion of causality. So we will try to go into this, and we'll see that in some cases maybe we can reconcile this information theoretic notion with the ordinary relativistic notion of causality. But as we'll see today in the talk, it always maybe it's not possible to do that. And then there are some recent efforts that people have made to see how we can reconcile these two notions together. So broadly, what I will be discussing will be based on these two papers. These are the papers which first describe this quantum mechanics from the higher order quantum theory. Usually when we talk about quantum mechanics, we only talk about states, measurements, so on and so forth, channels, so on and so forth. But here they will talk about some exotic objects which are beyond these things. So I'll be discussing from this perspective. And in the end of the talk, I will go to the celebrated result by Oggian, Oreshkov, Fabio Costa, and Castlev Brukner. So, which is this quantum correlations with no causal order. And there's one more paper which came after that, which are the simplest causal inequalities that you can get. So, our goal today would be to understand what is the meaning of this causal inequalities. So, yeah. So as I was saying, so I want to describe everything in the higher order quantum theory notion. So let's start with the most basic objects that all of us know. So that is basically one of the postulates of quantum mechanics. That is that every state can be described by a density operator. And the set of density operators of some system A, I'll denote it by some TA. So one more thing I want to say here is I want you to pay attention to the colors of the different shapes and symbols I'm using. So here I've drawn the row in an orange color. So states I will always be drawing in orange color. So next element immediately that we are introduced to are the POVM elements. So those I will represent by these blue circles. So these are nothing but the positive operators on some associated to some system A, which belong. So for every system you have some associated Hilbert space, and these are the set of positive operators on that Hilbert space. So after this, we come to even more dynamic kind of objects. So here you start to see what are the transformations I can have on a given state. So here map lambda is some transformation of the linear operators of some input space AI, and the output space is AO. So the output of this lambda is some operator on the AO Hilbert space. Now this lambda, we demand that this transformation lambda should have some physicality in it, in the sense that if I feed in some density operator, I expect to get some positive element at the output. So this kind of maps are called positive maps. So this P of AI to AO is the set of all. I have a laser. Okay. So this P of AI to AO is the set of all positive maps. So the first demand we immediately put on this transformation is that it should map states to states, right? Or positive operators to positive operators. But you see, just keeping this demand is not always sufficient, because sometimes what can happen is if I prepare an entangled state, a bipartite entangled state, and feed one part of it in this map, then I might end up with an operator which is not positive on the bipartite space. So if we demand this additional condition on lambda, we say it's completely positive operator and a completely positive map. Moreover, if it's guaranteed that all the density operators which have trace 1 are actually mapped to density operators which also have trace 1, then we say this lambda is completely positive and trace specific, which we also call as channel. Okay, so far I think everyone knows this much. So let me, yeah. So one thing I wanted to mention: why is this completely positive demand required? Because from this Perez-Horodoky criteria, we can show that there are some maps which might be positive in this sense, but when you feed in some entangled state, you get some negative operator or a non-positive operator in the output. All right. So let's go a little bit towards the direction of higher order quantum theory. This is where this starts. But before going there, I want to give a different kind of understanding of states and measurements. So what you can do is, if you take this POVM element, you can think of a POVM element as a map from some Hilbert space to a trivial Hilbert space. What I mean by trivial Hilbert space which has one dimension, which is essentially the complex numbers. So I can just define the map pi by just defining this trace rule. So essentially I can think of pi as a map from the operators in AI to linear operators in complex numbers. And linear operators in complex numbers are nothing but complex numbers itself. So essentially the output here is just a number, a complex number in general. And if I input a positive operator in, then I will get a positive real number outside. So thus this pi is a positive map. Moreover, I can also feed in a bipartite state and get the output in this fashion, where I trace over only one part, and I can see that effectively the output state that I get here will be the updated state in the system R. So that's why this pi can also be thought of as it's also a completely positive map. So nextly, on the other hand, you can also think of the density operators as maps. So but here you have to reverse the role of input and output. Here the density operators can be thought of as maps from the trivial Hilbert space to some A0 Hilbert space. So and in the trivial Hilbert space, you basically have only one operator and scalar multiples of this operator. So what it is essentially doing is just taking this operator and giving the state rho. So density operator rho can always be thought of as a map. That's why I have put it in a green box here. So again, you can see it's positive operator, and complete positivity is even simpler to check, because since this Hilbert space is of trivial dimension, I can't really have entanglement here. So the best thing I can do is send some product state here, and again I will get some positive states as output. So rho can be thought of as a completely positivity space. And if I move to measurements, then if I complete these measurements, then the summation of these pi will form will make an identity operator from the Hilbert space, and in this case, that measurement map can also be thought of as a completely positive space. All right. So what we have shown here is states and effects of quantum systems can be thought of as dynamical quantities. In this sense, at least, in the complete mathematical sense. All right. So now let's go to some exotic objects. Let's say I want to see what is the most general transformations I can do of linear maps. So I take in some linear map which has input AI and output AO, and this transformation S acts on it, and it gives you an output linear map which possibly has different input-output dimensions. So we want to study these kind of objects. So what I will do is I'll represent this object in this particular fashion. So this is just a diagrammatic representation for now. Why? Just for convenience, because what I can do is I can think of this S having 4 different ports. I input the lambda in this S in this fashion, and effectively I get some map from BI to P. Right? So this is what it's called a higher order transformation of maps. All right. So again, we should demand some physicality out of these maps. So what we want is that if you insert some completely positive map inside S, sorry. Yeah. So if you insert some completely positive map inside S, we expect the output to be completely positive. In this case, we will the output, if the output is also belonging to completely positive maps from BI to BO for all inputs, all CP inputs, then we say that S is a positive map. So we will also use the word supermap sometimes, because since it's acting on maps and giving you other maps, it's called a supermap. So in this case, we will say S is a positive supermap. And we still have not completed their demand of physicality, because what can happen is we can also feed in a bipartite channel or a bipartite CP map as the input of S, where I act S only on one particular part of the bipartite map. And we demand that even this should give you the output, which is CP. And this should happen for all inputs lambda CP. That means irrespective of the dimension of AI prime and U prime. So for all such lambda CP inputs, I should expect the output to be completely positive. And this map will be from AI prime BI to AO prime BI. So in such a case, we say that S is completely positive. Like just in the case of maps, we had a positive, but yeah.
So
Yes,
there is
yes.
a question.
Yes,
from
yes,
Anjali.
yes.
He has
Yeah.
written in the chat. I would say that please unmute yourself and ask the question. It would be more convenient. Shom.
Mhm. Yes,
Oh, okay,
go
okay.
ahead.
So okay. So I will just read the question. So he
Yeah.
is saying that we can also say states and measurements are dual in the sense that for measurement, the domain is quantum state space, range is complex field, and for states, domain is complex field, and range is in the quantum space. No.
Yes, means yeah, it's right. So so yeah, if you take some positive operator, like if so the dual, so if you take all the positive operators, its dual is again set of all positive operators. Yeah.
Can I say
Okay, I guess.
something over here?
Yeah.
Yes. To answer this question of Som, just it is this in this way that if you take the state space and then if you take the measurements, they are coming from the effect space. So those are actually functionals which are defined, and the functional space is actually dual to the original vector space. So in that particular sense, they are dual of each other actually, the state space and the effect space. Rather, we should call it with the effect algebra also. Sometimes it is called as effect algebra. So basically, those are functionals, and the space of functionals also forms a vector space which is dual to the original vector space. So they can be considered to be duals in this particular sense. It is not because of the domain and range only. It is because of this particular factor.
Yes. Thank you. So essentially, the trace operation is doing the mapping to the field. Right? So if you have a pi, which is a positive operator, it can be thought of as a map on every other positive operator, so, by the bond rule, and you get some element in the field. Yeah, thank you. So is that okay? Can I continue?
Yes, please continue.
Yeah. So as I was saying, so yeah, so we demand that whenever I apply this super map on one part of the bipartite CP map, I should also expect the output to be CP. So, but still, we want this much is not enough. We want some trace preserving kind of condition also. So we say that if the bipartite input map is CPTP, then the output should be CPTP. And in this case, we will say S is a valid supermap or a valid superchannel. So this is what is the definition of a superchannel. All right. So now what we can do is we can go, let's say, even further. I want to give the most general map from the set of supermaps to set of supermaps. So I have some object Y which takes in some supermap and gives you another supermap. So we can go in this direction and we can go as much as we want, but I'll not go in this direction because I want to introduce the idea of process matrix. For that, we will go in a little bit different direction. Either we can ask, okay, let's say I want to construct an object, which is a transformation from a pair of maps to another map. So I want this kind of object, and later I will put the demand of physicality. But before, to define process matrix, we can actually go even simpler. We say that, all right, I want to map a pair of maps to a number or a complex number. So just like in the case of POVMs, that's why I put the POVM case in the beginning. I want an object which can map a pair of maps to a element in L of C. This is some complex number. So you can also consider a simpler case where you can map just a single map to a complex number, but this is not that interesting as of now. We will be needing the upper case. Okay, so here I'm just this is just to remind you that we can expect the outputs to be complex numbers with some maps as the inputs. All right. So this is the object we are interested in. So this object W, as I gave a diagrammatic representation for S, I'm giving a similar diagrammatic representation for W. So it has 4 ports, and I feed in 2 different maps, and I get an object which has no ports because finally I want to map this to a number. So that's why the resultant object doesn't have any port. All right, so this resultant object will denote by W of lambda A comma lambda B. So again, we start by saying that we want the physicality demand, that when I input the CP maps, we want the resultant object to be positive, as in the output that I get here should be some positive element in the complex number, which are nothing but the positive real numbers, or to be more precise, non-negative real numbers. Not only that, as I said earlier, we also demand that when you feed in some bipartite thing, then also we expect the output to be linear. So here also, we will demand that if you input some bipartite map on the A and the B part here, even then the output should be completely positive map. So here when I see that when I feed in these maps in W, I get a resultant map in this on the prime systems. So I demand that this particular output map should also be completely positive. So that is my physicality demand of W. And also we need the trace preserving demand. When I feed in the trace preserving bipartite maps, the output should be trace preserving. So this object, which satisfies all these physicality demands, is what is called as a process. All right. So this is where we go into this process matrix formalism. Now, you can ask, all right, if I have a process, all I know is this maps to some positive element in the real number. So what is actually happening here? That is what we want to see. So let's backtrack a little bit. Let's say I take a state and I have applied this POVM map on it, I get a positive operator. But I can reverse the role of rho and pi here. Like this. I can also think rho was the map and pi is the input, right? And get this out. Then I can also do something like this, where I feed in some POVM element on the B Hilbert space and some POVM element on A Hilbert space to a map. So there should be a green box here, right? So here I want, yeah. Sorry.
I have one question. So
Yeah.
previously when you described the state map, like the row map, it had
Yes.
the input space to be some complex number and the output space was some
Yes.
non-trivial Hilbert.
Right.
Why is it different here?
Both of them are correct, but since rho is also a density operator, so rho is also a positive operator. That's why I can think of it in this way also.
Okay, so now
now I'm not thinking of it in that way, but I can think of it in this way also, since it is a positive operator.
Okay, just from mathematical consideration.
Yes.
Okay.
Yeah. Is there some question?
Yes, there is one raised hand. Please.
Hey, hi Sahil.
Yes.
So you said rho is a positive operator, so you can think of it that way. But pi is not a density operator, right?
Yeah, that's right. But that's fine, no, because like if I have a map, it's not necessary that I feed in only states inside the map, because the maps are defined for all operators, right?
Okay.
Yeah. So for now, you can just think of it as, so there is a specific reason I'm changing into this notation, so that it becomes clearer what happens in this process matrix thing. So for now, you don't think of it. So don't think of this as something physical or anything. You can just think of it as a mathematical artifact, where I can just take a map row, which maps every POVM element to a positive element. That's
Okay.
yeah. So
Sahil, can I ask one question?
yes, is my
Can you go back to the earlier slide where just you introduced the back a little bit back?
Yeah.
More. Yeah. So now this W, you want to introduce an object that take two map and
Right.
give me a number, or more generally some another map, let's say. So same thing I can think, okay, instead of lambda map, if we take two density operator, okay, and I want a something object, then object is nothing but something most general entanglement basis measurement. Will it be the case?
No. What is the output? You want to give two density operator as input, and what is the output?
Two density operator to be input and one density operator to be as output.
So that will be a bipartite input map, but single output map, right?
Yes.
Something like bipartite input, single output map.
Yes.
So it's like a CPTP channel only, but which has two inputs and one output.
Two input and one output.
Yes.
And I'm trying to say now that those state, if they're part of a bigger state, each of them can be part of a bigger state. Then also that physicality demand also all these
Exactly.
And what I'm trying to say, this entanglement swapping is the kind of things if we allow further communication.
Exactly.
That you now want to generalize at map level.
Exactly.
Okay.
Yeah.
So at map level, some peculiarity will come, but now means indefinite. What about the thing is? But now you said density matrix also we can see as a dynamical object. Then what is that analogous thing? We can.
I mean, I don't understand. Means data analogous thing means.
No, I'm saying so when you considering at map level, then
Mhm.
W will bring some W will a very abstract kind of things that will bring some notion that which map is earlier, which map is later. That
Mhm.
notion will be
Mhm.
something very peculiar kind of things. So
Mhm.
why this is happening? Because the map is now dynamical process. Now their earlier later notion will be something superpose something kind of things.
Right.
But at state level, state also you are saying we can view as a dynamical process now in that
Mhm.
higher picture.
Right.
So what will be that indefiniteness in that sense? Is it a manifestation of again entanglement? The swapping that okay, this Alice and Charlie never meet together, but finally this entanglement get distributed between Alice and Charlie due to the entanglement swapping.
Mhm.
Maybe we can further.
Yeah, I understand. Yes. Yeah, we can discuss that.
Yeah, we can discuss. Yeah.
Hmm.
Okay.
Yes. So yeah, we are going towards here. So yeah, so there is little bit color notation here, but like keeping this in mind, this particular object in mind, I want you to see this. So what I'm doing is I'm feeding a pair of POVMs inside a bipartite density operator and getting a number. So this is like the bond rule with product measurements, right? So if I have a collection of POVMs of Alice and Bob, which add up to identity on their respective Hilbert spaces, then we think of this as local measurement of fine. Now, in this sense, I want to make the analogous picture on this side.
And
So
this picture in standard framework is the Bell scenario.
not exactly. So you have the pi measurements exactly. This is the nothing but the Bell scenario. You're right. So some local measurement of Alice and Bob, precisely. So now we want to go to the analogous picture here. So let's say I have a collection of CP maps of Alice, which add up to something called which add up to a CPTP map. So such kind of object, you can think of it as a quantum instrument. So you have something called as a quantum instrument. So it is very analogous to a measurement, but an instrument is something which gives you a classical output, but also an updated quantum state. So you have some measure quantum instrument of Alice and some quantum instrument of Bob. And what I want is that when I feed in these quantum instruments here, I will get some statistics for the corresponding outcomes of Alice and Bob. Let's say Alice performs this quantum instrument and Bob performs this quantum instrument. So as I was saying, if they add up to CPTP, then if I feed in this CPTP map in the W, I expect it to be trace preserving, which in this language, it will boil down to probability 1, or it will map to the real number 1. So that is the trace preserving demand here. Okay, I'm not proving that, but you can do the calculation and prove that. All right, so here, the picture I want to give here is basically that if you have a density operator, the POVM elements, you can think of them as a local measurement of the density operator. So here the quantum instruments, you can think of them as local measurement of the process matrix. That is the notion I want to build here. All right. So now what we want to do is we want to be able to see how these probabilities are being assigned, right? So in the case of on the right hand side, we already know how to do that. That is by a bond rule. But how to do it here? That is the question that we'll ask next. So this is where we come to the generalized bond rule. So Oreshkov, Costa, and Brukner, they have introduced this thing in their paper. So keep this thing in the back of your mind that we already know how to apply the bond rule. on some product measurement, on some shared state. Now you see, there is no immediate way to connect these two because here all my objects were operators. So rho is operator, pi v and operators. But here, this W is an abstract map. Even this lambda A, lambda B, everything is a map. So there is no immediate way for me to do this. So how to do that? So this is where this Choi-Jamal-Kautsky isomorphism will help us. What it says is that if you take some map from this Hilbert space to this Hilbert space, and you feed in a maximally entangled state, which has both parts as AI, and you feed in one part of it to this map, you get a particular object at the outside, which will be an operator in the input tensor output Hilbert space. So here this phi plus is basically taken as this unnormalized state on AI tensor AI Hilbert space, and the output will be basically you apply the lambda in one part of it, so you get the output in AI tensor AO. So this is the definition of Choi operator of the map lambda. Now what is interesting is that if you take the collection of all maps from AI Hilbert space to AO Hilbert space, and if you take the set of all linear operators on this Hilbert space, then you can show that there is a bijection between them. Not only that, if you take all this, if you take a subset of this, proper subset of this, which is all the CP maps, then you will see that the bijection will be to the positive operators on positive semi-definite operators on AI tensor AO. So why this is important? Because now we have found a way to talk about our local maps of Alice and Bob in terms of operators. So there is a way for us to give a prescription of the bond. So what I say now is that I have a local CP map of Alice, which is some positive operator in this Hilbert space, similarly for Bob. And now we posit some object, which you can think of it as the Choi operator of the map W, which will be some operator in the four-party Hilbert space. And this is where we get the generalized bound. So even the Choi operator of W will be again an operator in the four-party Hilbert space. So this is how I'll give the prescription of how this W is mapping to a number. Since I have converted every object to a operator. Yeah, sorry.
Yeah, Sahil, I had one question. So
Yes.
you have this CJ isomorphism for so where you show bijection between this map and linear operator. Can you also have some isomorphism between this super map and a map?
Yes,
With
yes,
some
yes.
bijection.
Yeah, you can have that. So those kind of things are there. So you can, so any complex object you think you can think of, it might be higher order map, it might be super map, super map. You can always give an operator as a representation for it.
Okay.
All right. So in this case, so we have some object JW, which will be of this form. Now, in the literature, usually they don't write J of W, they just write it as W. So I'll also follow that. But I want you to keep in mind that when I write it as a W here, it's different from the actual abstract map. All right. So if this is the case, now let's ask the condition again that, okay, what happens if I put the demand that this W is a physical object, as in it takes valid CPTP maps, which are bipartite to valid CPTP maps, like I said before. So what you can show is that if you take these operators in this way, so this is nothing but the process. What you can show is that if you demand all those conditions, you will be able to show that the Choi matrix of the W, which I denote as W, which is operator in the four-party Hilbert space, will be a positive operator. So it will, Another way to write that is this. And the trace preserving condition of W will tell you that it cannot be an arbitrary operator in the four-party Hilbert space. It has to belong to some particular subspace of that four-party Hilbert space. So what subspace it is not important for now. It's just that putting all these constraints, we derive some specific form of W. It is a positive operator and it lies in some particular subspace. That's all. So this object, which is actually the CHOI of the process, is what they call as process matrix, because now it's an operator. So this is the process matrix. So this is how we have the generalized bond rule. So the statistics of Alice and Bob, the probabilities with which they will generate the outcomes A and B, will be given by this generalized bond rule, and it has to satisfy all this physicality criteria. All right. So this is the trace preserving criteria. Yeah. So let's try to construct some examples of this process, because for now it seems like this object W is some very abstract mathematical object. So let's try to give one example which we are more familiar with. So that example you can give in this form. So imagine that you have Alice and Bob. Alice is applying her local CP map, or you can think some quantum instrument. It is part of some quantum instrument. And similarly, Bob. Now you have some state which enters Alice's lab. She performs this operation and sends the evolved state, which again evolves via some map N to BI Hilbert space, and then it is going to Bob. So you can think of it as there is some signaling happening from Alice to Bob via this channel N. So if you fix the instruments of Alice and Bob, the statistics that you get, the PAB statistics that you get, will be completely determined by the process matrix. And in this particular case, the only thing the statistics can depend on are nothing but the state row and the CPTP map in between. So this is not an exact equality. You can think that this kind of object where you have an input row and a shared channel between them from Alice to Bob, that constitutes to a process matrix. Okay. Now, here, this particular case that I have taken, you can see that there is some signaling happening from Alice to Bob. That's why I have given the notation A is in the past of B. So, like there are more kind of objects you can construct, where again you can give a is in the past of B interpretation to that. But this is one particular example. I am not discussing all those things. But there are many such objects I can construct. All right. Now, you can also have other kind of objects where you don't take any channel at all, just feed in a bipartite state to both of them. And they will again get some statistics. And in this case, you see their statistics will be independent of what the other party is doing. So this is what Manikda was talking about. So in this case, they will get a no signaling statistics. So these kind of process. So here again, you can see the only thing this statistics will depend on is the shared bipartite state row. So again, in this case, I can think that the process is this object. So you see, process is something very weird. Sometimes it is a shared bipartite state. Sometimes it is this state and a channel. So it is all these objects which gives you statistics on Alice and Bob's local city maps. So many such objects we can construct. So now we can ask the question, what kind of objects we can construct? So what you can show is that there are some valid processes which we cannot write as a convex mixture of these kind of processes that we talked about. So I have showed you an example of this one and this one, but you can also construct an example where Bob is in a past of Alice. So if you take convex mixtures of these kind of objects, there is some process W star which you cannot write in that form. So what's the big deal about it? What we know is that the W star is mathematically legit object because it is always completely positive and trace preserving. So what's the big deal about it? So this is where the OCB paper comes in. Yeah. Anyone has a question?
Yes. So this question, like I was wondering that in order to be making it to be physical, you are using this concept of complete positivity. So I was thinking of like if suppose we relax this condition of complete positivity, so there will be some positive but not completely positive supermaps, which can actually identify which process matrices are inseparable. That means which cannot be written as convex combinations of some separable process matrices. Can we bring in some idea of that type, inseparable process matrices?
You want detection, basically.
I want detection. So, but first of all, what I actually I'm trying to tell is that such inseparable process matrices will correspond to supermaps which are positive but not completely positive.
So yes, I means I have to think about it a little bit
Yes,
more.
yes.
I don't know exactly, but what you are saying, like these witness kind of things, people have constructed. So so since this set of all separable processes is a convex compact set, you can always find, due to this Hahn-Banach separation theorem, you can always find this witness for inseparable processes. But that part I have to see what you are saying, that whether the witness will be positive but not completely positive process matrix. That is your question.
Yes, yes. I'm saying that that means for each and every inseparable process matrix, there will be some kind of a positive but not completely positive supermap. That is what I'm saying. You can also think about this later on and say, because I think that such things will be there in order to, like, because for inseparable process matrices, the output might give rise to some kind of an anomaly, and for which I'm not using the word entangled over here, because you have moved on to a more general formalism called process matrices. So if I'm trying to say that it is kind of some kind of an inseparable process matrices. So that is what I'm trying to say. Okay, so maybe you can give it a thought after some time.
Yeah.
Yes. Okay.
Okay, we can discuss that. So, who was asking the question?
Yes,
it was me.
I'm Nirmal.
Okay. So yeah, so now we can ask, so what is the big deal about it? We have this object W star. It's just a mathematical object for now. So what, I cannot write it in this form. So this is where that paper comes in. They define a game, what is called as guess your neighbor's input game, and this game will serve as a device independent test of this W star for it to be
Sahil, moving to the next part, can I just ask a little bit one question?
Yeah, sure.
So go to the first part where this bell kind of picture is coming.
This part.
No, I'm saying state level.
Oh, that. Oh.
Then we'll go to process level. Yeah.
Yeah, that.
That one. So what is happening here on the row part, you apply a pi b POVM, and a part pi a POVM, and bond rule is giving us some outcome probability. And rho we have assumed it is a operator or density operator on HA tensor HB.
Right.
Let's say we don't assume that. Let's say rho is an object in some big Hilbert space H. And Bob is applying some POVM, set of POVM, which is forming an algebra
On H,
on
subalgebra of H.
subalgebra of H, and Alice is applying another subalgebra, and Bob's algebra is commuting with Alice's algebra.
Yes.
Then we got this commutating correlation set.
Hmm.
Okay.
Yeah. But for finite dimension, it will be same.
Finite dimension it will be same in general, but we can come up with something very peculiar. In infinite dimension, it is different. That is some recent result. Let's try to ask the question in this level. So here also, I'm thinking, okay, here also you see you have on this all these things are a tensor product structure has been assumed.
Yes.
Let's assume there is some very big algebra, and Alice has some set of CPTP map, and since all these CPTP map due to this CJ, we can consider as a positive operator, means as an algebra.
Exactly.
So Alice has some subalgebra, Bob has some subalgebra,
Yes.
and now
They
should we impose the condition that Alice's algebra should commute with Bob algebra?
Yeah, that we should not impose the condition, no?
That's the peculiarity here, no? Because
No, but
here,
yeah, I understand what you're saying. No, but you are saying the commuting thing captures the no signaling demand. But here some signaling is
in a
happening.
sense, commuting things actually captures no signaling demand. But here some signal also I want to capture. Then how to this commuting picture we should generalize?
Yeah.
We can think about it. Which means, I don't know. Means, but in CJ picture, it is a subalgebra, no?
Yeah, I understand. Means you are asking again, is it possible to get non-tensor product structure at process matrix?
Yeah. Or maybe I can ask you in this way. Let's say as you said that process matrix is capturing channel, capturing density matrix. But okay, commuting correlation, of course it will capture because signaling is very powerful thing. But how to generalize at process matrix level?
Actually, for these kind of questions, we need to know this operator algebra. Means in quantum mechanics, like in the left hand side picture, we know that there is a gap in this correlation
because space-like separation is there.
Yes. Yeah, but I don't know whether there will be gap in process matrix correlations also.
Yes.
Yeah, I understand the question.
Yeah. Okay, we can discuss later. No problem.
Yes. I mean, Sahil, you have like around 5 minutes. So after that, we can have.
I'm about to finish. I'll introduce the game and I'm just about to finish. Yeah. So they came up with this game called Guess Your Neighbor's Input Game. So for now, you can forget about all these things. What you can just keep in mind is we have some W star which satisfies all these demands and which cannot be written as convex mixture of these objects. So suppose you have Alice in her lab who tosses a coin, and let's denote the output of her coin by X. And similarly, Bob, his output is Y. And they want to guess, Alice wants to produce a guess A for the state of Bob's coin. And similarly, Bob wants to guess Alice's coin. So the winning condition of this game is that this A should be equal to Y and B should be equal to X. So you can see that, okay, if you allow them some communication, then it's very easy to win this game. Alice will just inform Bob and Bob will inform Alice. So they can just communicate with each other and do this task perfectly. But there is some constraint that they assume for the local lab. That is that once some system enters Alice's lab and it leaves Alice's lab, you cannot again take information from the environment. So the lab will open only once. She can perform some operation on the system which is entering her lab, which might be an operation dependent on X. She can get some outcome A and send the evolved state out. So information once left from Alice's lab, new information cannot enter again. So this is what they call the closed laboratory assumption. So under this assumption, you can see that once Alice communicates, so suppose Alice starts the protocol and she communicates to Bob, and Bob gets to know Alice's coin state, he cannot communicate back to Alice because Alice's lab has already been closed. So in such case, when you assume that Alice and Bob are two events, means their operations are are localized events in some definite space time, then as in this kind of structure, then your success probability will always be bounded by half, because Bob can know perfectly, but Alice has to guess the state, in which case she will be right only half the times. So this is what we call the causal success. And you can show that no matter what is the kind of relation between Alice and Bob, if it is any of these three types or their convex mixture, then the success will always be bounded by half, and they cannot win perfectly. Now what they show in this paper is for this kind of game. So this game is not the actual game in the OCP paper. It is a little bit different variant of the game from Cyril Bransiel's paper, and they have shown that these kind of objects, which we saw before, will give you a success strictly greater than 0.5 or half, but any separable process will always give you bounded by half. So that is the weird thing about this, that this kind of object, I cannot interpret it in these three pictures, in this kind of picture. Like I have to think of it as a completely different object. So this is what they call as indefinite causal order, because there is no definite causal order that you can prescribe to this W star. And when this particular W star is giving you more success than 0.5, this is what they term as violation of the causal inequality. And this serves as so as long as you satisfy all the assumptions. So there is one more assumption I didn't mention about, which was the free choice assumption of Alice and Bob. That is, the coins that they toss are independent of everything. So if you take all these assumptions and the closed lab assumption, then this serves as a device independent test for this W star, that it is indeed a indefinite causal ordered object. I think you cannot give any ordering between Alice and Bob, as in who is acting first and who is acting later. So if there is some question, let me just finish this last slide. I'm almost done. So
Yes,
what you can do? Yeah.
No, finish it and then you can take the questions.
Okay. So what you can do is that here you get these correlations. So when Alice and Bob perform these X and Y dependent instruments in their lab, so Alice is indeed allowed to perform the X dependent instrument because she has the knowledge of her coin state. And similarly, Bob. So they will get some correlations, P, V, X, Y. So the interesting thing here is, unlike the Bell scenario, these correlations now can be signaling correlations. So in Bell scenario, you always get no signaling correlations. So what you can ask is, what is the structure of these correlations? So on one side, you have the correlations, which are in this green set, where Bob is never able to signal to Alice. So these are those correlations in which Bob cannot signal to Alice. So I have written it as Alice is in past of Bob, but just because Alice is in past stop Bob, it might not mean that there is some communication happening. But you can guarantee that there is no signaling from Bob to Alice. And similarly, you have the other set where Alice cannot signal to Bob, and the intersection is the no signaling correlations. This is the no signaling polytope that we are familiar with. And their convex hull is defined as the causal polytope. The convex hull of all this is the causal polytope. And the points which are outside this is what we get from this W star kind of objects, which are the indefinite causal order objects. And the outermost set that one can consider is what we call the two-way signaling polytope, which is basically all the correlations that you can get, in which you can signal as much as you want in either direction. So now the question becomes that what kind of correlations are possible to achieve by, what kind of two-way signaling correlations are possible to achieve by indefinite processes? So we don't know the answer to this question. So this is a very big open question in this field. And there are some papers. Recently, there is a paper on arXiv, like in last 6 months, in March. So by Giulio Chiribilla, they are trying to capture what kind of correlations or what are the bounds of causal inequality that we can get from this process matrix framework. So analogous to the Cyril-Singh bounds in CHSH in Bell scenarios. So from here we can ask the questions that, so like I don't have the time now, so the next time I will be discussing this paper and what we are currently thinking, our group, we are thinking about in this direction. So we are thinking about what kind of physical principles we can give which bound the quantum process matrix correlations. And yeah, so that's it. Maybe I can continue with the questions. So it's, and
Yes,
so one more thing I wanted to mention that like in future, if I get some time, I would like to discuss this paper. But okay, this is another paper by Renner and Vilasini. So this is about the two different notions that I mentioned in the very beginning, the information-theoretic notion and the relativistic notion of causality, how to reconcile this, because what we saw is that from the information-theoretic notion, we get some objects which cannot have a causal explanation. So what this paper is trying to do is it possible to reconcile these objects with the relativistic notion? Yeah. So
yes, I mean, definitely you will have time because next week also
yeah,
you are talking.
yes.
Okay, so questions. We had Shumit's question. Shumit, you can unmute yourself and ask, and later we will have more questions. Okay. I see all of you raising hands.
Yes.
First, Shumit.
Sahil, I have a minor question or a comment, as you may. So usually in DI scenario, we do not assume anything from the device, as in Bell case or any other games that one can think of. But here, since quantum mechanics is assumed as an inherent theory, does this inequality, sorry?
Assumed as a what?
As a theory of the system that we are performing experiment over. Unless this is a classical bound as well, or say without assuming anything about the device, I don't know of any result as such, but you may be more aware than me, so I have a question in this regard.
I think maybe,
yeah,
that's what let's say maybe I was not very precise here. So you're right, we need to, so since we want a device independent test, we need to show that if, so this bound that I have written here, the causal bound, this is something that you can derive independent of the theory, as long as you satisfy the closed laboratory assumption and the free will assumption. Right?
Okay, my theory does not need to be quantum mechanics whatsoever.
There is no such thing. Moreover, that's correct. But moreover, after you get a violation. See, in this particular case, how do I derive the violation? I am deriving it from a particular W star and some particular CP, some instruments of Alice and Bob, and I'm showing that it has success more than 0.5. But this is me prescribing a protocol to you, but actually the protocol and the objects inside doesn't matter, because the success probability is only dependent on the statistics. Now, as long as my statistics is such that the success is strictly greater than half, I don't care what you use to get those statistics. That object must be indefinite causal order. So that's why it's device independent.
I see.
Okay.
Is it
next
answering
question.
your question? Okay. Are there any other
Yes.
questions?
Yes, Samrit, you can ask your question.
Hey, Sahil. From what I could understand, this process matrix is the choice of the process. Is that correct?
Yes, yes. So
So,
it is, means the word is
yes.
used interchangeably. Like they don't actually call it showy of the process and all. When they say process matrix, they mean this object, but they are equivalent. So yeah.
Okay, because does the properties of like in Choi isomorphism, when we talk about it, like there are some things like how you if you have this Choi matrix, you can get the action of the channel using some equation and
Mhm.
also if you have composition of channels, you can use a certain I think it's called link product or star product to get the if you have the choice of the two channels, you can get it using link product. So does these properties carry over to this process matrix formalism as well, or is it like the same
Yes.
product?
Yeah. So yes, what you are saying is right. So here this octagon that I have drawn. So this is the abstract map which we call the process, and for every process you will find some CJ operator corresponding to it, which will be called the process matrix. And for every valid process matrix that you write down, it will be some particular map of this form. Yeah. So there is this isomorphism there also.
Yeah,
And
but is the isomorphism the same as in Choi isomorphism? For example, like if you have composition of two process matrices, uh, can we composition of two processes? Can we take the link product of these two process matrices to get the process matrix of the composite process? Or
yes,
is it like
but
some?
see the so like when you say composition of process matrices, you have to be precise what you mean, because
Okay.
because sometimes when you ask, let's say I have two states, I want to take composition of the two states, but what do you mean by composition of two states? Are you sorry, I have two channels, I want to take composition of two channels. So you can take the composition either in a series or in parallel, right? Like
Yes.
either one is acting before the other or they are parallel. So what happens here is that parallel composition of processes is not always a valid process. Okay.
I see. Okay.
And there is some justification for that also, why that is the case. But series composition also, people have done some work. Series composition in the sense that suppose I have this process I, and I can take another process which is in the future of this process, like which is completely in the future of this process, and those kind of composition you can take. And I think mathematically some things might be there, what you are talking about, this link product and all these kind of things, because link product is very natural language to denote all these things. Even this trace rules, etc., what you use, all of them are nothing but the link product. Where I have written the trace rule. Yeah. Here, this trace rule is nothing but the link product of this choi with the link with the CPTP maps of A and B. Yeah. So
Okay.
this
Okay.
like
Yeah.
link product is very general thing. So for special cases, it boils down to trace role and all this.
Okay.
But
Okay.
yeah.
Yeah. Thanks.
Okay. Are
So
there any questions? Okay. If not, then let us thank the speaker, and we will wait for the next part of this series. Okay. So thank you everyone for joining. So I will stop recording now.
thank you, Manika.